Hello, my name is Skrimponis and I'm a PhD student at NYU. And today I'm going to present to you our work regarding power consumption analysis for mobile millimeter wave and sub-terahertz receivers. One of the most significant technical barriers in the realization of millimeter wave communication systems is the power consumption, and especially for the handheld devices. Due to the high isotropic loss, millimeter wave communications rely on narrow, electrically steerable beams. As a result, in order to enable beam steering, the front end must support a high number of antennas at a very high bandwidth. And in this work, we also look on higher millimeter wave bands, above 100 GHz, which are usually referred to as sub-terahertz, and we assess the feasibility of a UE device with the current technologies in order to identify future areas of research. We also compare different beamforming architectures, such as analog and fully digital beamforming, for a multi-carrier new radio system. Now let's look in the system design. We start from a 3GBP NR system with component carrier aggregation because of the flexibility of the standard provides a very good baseline for a 6G evaluation, enable us to partition the processing for each one of the component carriers independently, and allow us to allocate the bandwidth depending on the capabilities of the UE. On the table on the right, you can see the parameters for a practical deployment at 28 GHz and for a hypothetical system at 140 GHz. We took some reasonable approximations, such as the number of antennas, because the number of antennas at 140 will occupy the same physical space as the one at the 28 GHz. And we also used two digital streams per component carriers because of the system, which lacks in spatial diversity. Now, let's take a look on the architectures of the different beamforming systems. First, we have the fully digital beamforming, where in this system you can observe all of the analog components drawn in blue and all of the digital components drawn in green. In the fully digital case, we have NRX antennas, and for each one of the antenna, we have a dedicated LNA, mixer, and ADC. In each antenna, there are NCC component carrier selection filter, which are used to extract each one of the component carriers. The output of the NRX ADC for each component carrier is fed to an NRX input NSTR output linear digital beamformer. The digital beamformer eliminates the need to run one FFT for each antenna, and instead we run per each stream. As a result, each one of the streams is then fed to an FFT agent for the OFDM processing. Also, the PSS searcher is run to one component carrier only per antenna. Next, we have the analog beamforming architecture, where we have NRX antenna, and the signal from each one of the antenna is passed through an LNA, and then we have one RF phase shifter per stream. Then the streams are combined, and a mixer is used to down-convert them to baseband, having one pair of ADC per stream. In each stream, there are NCC component carrier selection filters, and similarly to the fully digital beamforming, we have one OFDM processing per stream per component carrier, and we also run the PSS searcher to only one component carrier per stream. Now let's take a look to each one of these components individually. First, we have the LNA. The LNA design can be very challenging for millimeter wave due to the very low noise figure requirements. Using the following equation, we can calculate the DC power drawn by the LNA based on the gain, the figure of merit and the noise figure of the LNA. In both of the designs, we consider NRX LNAs, and that the LNA must apply to the system at least a gain of 10 dB. However, in the analog case, each one of the LNAs drives NSTR phase shifters, and each one of the phase shifters has an insertion loss which we need to compensate, and this will increase our power consumption. One of the assumptions we make is that the insertion loss of the phase shifter does not change from 28 to 140 GHz. Our next component is the mixer. In our analysis, we consider the mixer as a passive device. As a result, the power drawn by the mixer is by the LO generation network. In our analysis, the LO supplies NRX mixers in the digital case and NSTR mixers for the analog case. In the two systems that we analyze at 28 GHz, we considered an LNA with a noise figure of 3.1 dB and an LO power of 10 dBm. For the 140 GHz system, the LNA has an almost 10 times worse noise figure and a much higher LO power. Our next component is an analog to digital converter, and the power consumed from the ADC can be given by the following formula, which depends on the sampling rate, the number of bits of resolution, and the energy per conversion step. In the fully digital case, we use NRX 4-bit ADC pairs, while in the analog we use NSTR 8-bit ADC pairs. And this is due to the fact that the SNR degradation can be compensated by the beamforming. One component that is very crucial to our analysis is the component carrier selection filter. Thus, the design of this filter is of prime importance. On the right, you can see the frequency response of a proposed component carrier selection filter. This filter is designed using the multiple filter design tool, where we have 65 tabs with 6 bits of coefficients and the stopper rejection of about 30 dB. In the graph, we can observe the passband region, which is up to the black dust line, and the stopband region, which starts at the red dust line. The 6-bit coefficients are multiplied by the 4-bit ADC outputs and accumulated with 12 bits. The power consumed by the component carrier filter in the fully digital case depends on the energy per real MAC operation, the length of the filter, the number of receive antennas, and the sampling frequency. While in the analog beamforming case, it depends on the energy per real MAC, the length of the filter, and the number of streams and the sampling frequency. The following results are generated using the spiral code generator and the Synopsys DC compiler and indicate around 100 femtojoule per real MAC at 28 GHz and around 50 femtojoule per real MAC at 140 GHz for the fully digital architecture. Similarly, it can be observed that for the analog architecture requires 178 femtojoule per real MAC at 28 GHz and 88 femtojoule per real MAC at 140 for the analog architecture. In the above results, we assume larger number of ADC bits for the analog architecture and that 140 GHz power should be less since the required SNR per antenna is lower. The fully digital beamforming design also requires a linear digital beamformer which multiplies the inputs from the NRX antennas to NSTR digital streams. In each sample, it must perform NRX NSTR max. Since the total sample rate across all of the component carriers is f samp, our initial power estimation using again the spiral tool based on the 6-bit real input from the component carrier filters is around 1 picojoule per complex MAC operation. Similarly to other works, we found that the PSS search can be implemented using very few bits. At this resolution, the PSS can be implemented in time domain, and initial calculations show that the power is negligible. At this point, we are still evaluating the power required of the FFT engines for the OFDM processing. However, it will be the same for both of the designs. Now let's summarize the power consumption estimates for both of the designs. First we have the LNA. While in both of the designs we have NRX LNAs, it can be observed that the power consumed in the analog case is much higher, and this is due to the 10 dB insertion loss for each one of the phase shifters. Then we have the mixers. If you may remember, in both of the designs we assumed passive mixers, and in the fully digital case we have NRX mixers, while in the analog case we have NSTR mixers. Next component are the ADCs, where we have NRX 4-bit ADC pairs for the digital case and one 8-bit ADC pair for the analog. In the fully digital we also have NRX NCC filters, while we have NSTR NCC filters for the analog. Last but not least, we have the fully digital beamformer, which performs an NRX NSTR linear digital beamforming, and it is not used in the analog case. So as a summary, you can observe that at 140 GHz we require around 7 watt, which can be prohibitive for a handheld device. We can also observe that for the fully digital, the component that dominates the power consumption is the LO, while in the analog case, it is the insertion loss from the phase shifters. As a conclusion to our work, we provided some initial power estimates for a 64-element 140 GHz receiver, which consumes approximately 7 watts, which is prohibitive for a handset device. And even if someone power optimizes some of these components, the power will still be high. We estimated it will be around 2 to 3 watts, which might be available in other scenarios like robotics cars and UAVs. We also observed that the figure of merit of the 140 GHz LNA is almost 10 times worse than the 28 GHz, which indicates that the future research will improve the power consumption in high-frequency devices in order to widen their applicability. In the fully digital beamforming architecture, the power drawn from the mixer and the LO is dominating. And we also can drop the baseband power with aggressive bit-width reduction. While in the analog case, the power drawn from the LNA and the phase shifter dominates. Thank you very much for your attention, and if you have any questions, please send me an email to this address. Thank you.